Okay, so what we're going to talk about now is sequences and series. It's chapter 5. And the whole point of doing this is because we're going to we need to set a bunch of foundation so that we can work with something that are called Taylor polynomials. So to give you an idea of like why this is useful, like let's say we wanted to compute the sine of, I don't know, 13.8 degrees. Like, does that make sense? You want the sine of 13.8 degrees. Now, obviously you would have to convert 13.8 degrees to radians and then compute whatever that is. Now here's the problem. Do you actually have like a formula that you can plug 13.8 into and actually get what the sine is? No, but somehow your calculator does that. So to actually get a formula that you can plug 13.8 into, or whatever 13.8 is as radians, we have to come up with a way to figure out, like, it would be like, I'm just going to make this up. Let's say the formula was 1 plus x plus 1/3 x squared plus 1/4 x cubed plus 1/5 x to the fourth. Like, you could actually plug something into that x, right? 1 plus x plus something x squared plus something x cubed plus something x to the fourth, and compute that. You can actually find out a formula for any function, whether it be sine, cosine, tangent, or the exponential, that looks like a polynomial. So we have to sort of like talk about a bunch of random stuff so that we know enough to figure out how to do that. Okay, so we're going to start off with sequences. Okay, so whenever we talk about a sequence, just skip over chapter 4 for now. We're in chapter 5 now. So whenever we're talking about a sequence, we talk about the terms of the sequence: A1, A2, A3, A4, A5, and so on. And then you do ... AN ... So a sequence is literally just a list of numbers that are in order. So this is called the sequence of A. You have the 1, the 2, the 3, the 4, the 5, the n. That's called the subscript. That tells you which number in the sequence that it is. So the 1, the 2, the 3, the 4, the 5, the n. So that tells you which number term you are talking about. So the terms are the different numbers in the list of your sequence. The subscript says which place in the sequence that particular term shows up. Okay, and then if you want to talk about an arbitrary term, you use usually the subscript n or I. So an is the nth term. Okay. And then usually instead of writing it like that, what we'll do is put curly brackets, a subscript n, curly bracket, and then you say like n equals 0 to infinity. Does that make sense? That tells you that this is a sequence that starts at the first term and has infinitely many terms. Not every sequence need have an infinite number of terms. Like maybe you have a list or a sequence that only has 20 terms. So you would say like an, you'd put the little brackets, n equals 1 to 20, right? That's a 20 term sequence. Okay, so you can have a finite sequence or a partial sequence and then an infinite sequence. Okay, cool. So the n might also be called an index variable. Do you remember how for sigma notation we had the index variable or the summation variable? Now we have an index variable, same exact thing. Okay, cool. So you have these different terms. Oh, okay. Now, how do you actually come up with the numbers in the sequence? There are two general ways to do this. I can give you what's called an explicit formula, or I can give you something called a recurrence relation. Okay. Start off with like an explicit formula first. Or actually no, we'll start off with the recurrence relation. So, does everyone remember arithmetic sequence. Like it starts at some number like 5, and then you'd have 5, 7, 9, 11, 13, and so on. Okay, so how does an arithmetic sequence work? You start at some number 5, which would be your A1. The 7 is the A2, the 9 is the A3, the 11 is the A4, the 13 is the A5, and so on. But, so, let me write how the recurrence relation works. So to write this as a recurrence relation, you would write the little brackets, and you'd say the first term, A1, is 5. And then what you do is you give a way to get to the next term of the sequence. So I'm going to talk about the term an plus 1. So if you start at 5, what do you do to get to the next term? Or add 2, right? So A2 is A1 plus 2, right? And A3 is A2 plus 2, and so on, right? So do you see how once you have the first term, the way you get to the next term is by adding 2. So the nth plus 1 term is the nth term plus 2. That's what a recurrence relation is. It tells you the starting term, and then it tells you how to level up to the next term forever and ever and ever. The an plus 1 equals an plus 2 tells you how to start at the nth term, like the first term for instance, and then it tells you how to get to the second term. And then you can use the second term to get to the third term. And then you can use the third term to get to the fourth term, and so on forever and ever. Okay, so this is sometimes called the recursive formula as well. This is how recursion works. You get the nth plus 1 term in terms of the nth term, the previous term. Okay, now, well, what about an explicit formula for this? The explicit formula is the nth term is the first term plus n minus 1 times 2. So the way you get to the nth term is you take 5 and you add 2 times n minus 1. And let's check this by trying to compute the 5th term. According to this formula, you would do 5 plus 2 times 5 minus 1, right? Because your n is 5, a5th, the n is 5, which would be 5 plus 2 times 4, which would be 5 plus 8. And what's 5 plus 8? 13. And if you look at the 5th term, what is the 5th term? 13. So this is here is the explicit formula. This here is the recursive or recurrence formula. There's an important difference between them. The explicit formula allows you to plug in 5 and get the 5th term. The recurrence relation, or the recursive formula, does not allow you just to plug in 5. You start at 5. It doesn't allow you to get straight to the 5th term. It tells you the first term is 5, and then it tells you how to get to the second term, which is 5 plus 2, which is 7. And then it tells you how to get to the third term by taking your 7 and adding 2. And then does that make sense? Like, you have to keep on going one at a time, one at a time, one at a time, one at a time. Sometimes one of them is more useful than another. If you want to just get to the 5th term, the explicit formula is very useful. However, when you're actually analyzing things, usually the recursive formula is more useful to like figure random stuff out about the sequence. So let's do one more example. Hopefully you guys remember the geometric sequence. Okay, so if you start at a number like, I don't know, 3, and the next number is 6, and the next number is 12, and the next number is 24. Yeah, exactly. So you have your A1, your A2, your A3, your A4. So it's easy to come up with the recurrence relation. The first term is 3. The nth plus 1 term is you take your nth term and double it. Right? How do you get to the next term? Multiply by 2. You can also come up with the explicit formula. It's 3 times 2 to the n minus 1. And let's just plug in some numbers, like let's get the third term. According to this, the third term is 3 times 2, 3 minus 1 is 2. 3 times, that'd be 3 times 4, and what's 3 times 4? 12, and if you look at the third term, what is the third term? 12. Okay, and like what I was saying earlier, sometimes the recurrence formula is better, sometimes the explicit formula is better. Okay, any questions so far about the difference between the two of them? For either of these so far? Is that like, yeah, things we want to ask? I'll pause. See if there's anything you want to ask. Okay, cool. So, often what we're interested in is the limit of a sequence. Now, what do I mean by this? I mean, let's say you have some sequence of ANs, and you're wondering like, oh, hey, what happens as n goes to infinity? So in other words, as I go towards the end of the sequence, do the terms have any pattern? So in other words, as we head towards the end of the sequence, do the numbers head towards a particular number or not? Okay. So let's give you an example. So usually to do this, you need an explicit formula, just to let you know, right? That AN is just like code word for the formula, the explicit formula for the nth term. Okay, so this AN right here is just the formula for the nth term. In other words, the explicit formula that I told you about. And basically we're saying, like, look, as you keep on plugging more higher and higher index into there, are you going to a particular number or not? So let's say that, let's come up with one. Let's say that your AN is 1 plus 1/2 to the n. Now, do you think that we should plug all this in by hand if we want to see what happens as n gets bigger and bigger? Do you want to plug bigger and bigger values of n by hand into here? No. What should we use instead? Oh, Wolfram, yeah. So you can use Wolfram to do this for you, so I'm going to switch over to Wolfram. Let's erase all this junk. Okay, and what you can do is you can say, hey, I'm going to have a formula, A of n, and then you have to put the underscore. right? So do you see how here your index variable is n, your function's called a, and our thing was 1 plus 1/2 to the power of n, right? Boom. So if I wanted to figure out the first term, I could put 1 in here, right? So what's my first term? 3/2. I could figure out my second term by plugging 2 into here and so on, right? Okay, but should I bother by plugging in 1 or 2? If I want to figure out a bunch of terms, what command should I use? Do we remember? If you want to like plug a bunch of different numbers into a function, what's the command that you should use? Do you remember? Do you remember? Anyone? If you want to plug a bunch... Have I told you how to do this? I don't even remember, to be honest. I'll just tell you. It's called the table command. Oops, sorry. This is really hard with the new keyboard. So you do the table command and you tell it, hey, I want you to plug stuff into this function an, and then you put curly brackets, and you tell it, hey, the variable you're going to be plugging into is n, and you put a comma, and you put some more curly brackets, and then you give it the numbers that you want it to plug in, such as like 1, 2, 3, 4, 5, 6, and so on. So I'm going to run this, and you can see that if you plug 1 into the formula, you get 3/2. If you plug 2 into the formula, you get 5/4. If you plug 3 into the formula, you get 9/8. If you plug 4 into the formula, you get 7/16. Now, to make this become a decimal, you put / uppercase n, and so you can see that my first term is 1.5, my second term is 1.25, my third term is 1.1.25, then 1.0625, 1.03125, 1.01563. Okay, what does it look like these numbers might possibly be going towards? Like, you could put in another in there, and you can like say, like, let's have it plug in 100. Yeah, so let's have it like find the 100th term. Like, if by the time you plug in 100, it even rounds down straight to 1 for you. Okay, so that's one way you can do it. It's actually sort of smart. If you write the table command, and you write that I want it to plug into the function an, what you can do is you can tell it the variable, and you can tell it a starting point, an ending point. Let's go to 1000. And then you can tell it how much you want to increase each time by. Oh shit. Sorry. Sorry. I'm having a hard time typing. Okay, so what this is telling you is I want to start at 1 for n, and I want you to plug in all the way up to n equals 1000, but I don't want you to go 1, 2, 3, 4, 5. I want you to add 10 to n each time. So I want you to start at n equals 1, and then the next one will be n equals 10, and the next one will be n equals 20, and the next one will be n equals 30, and the next one will be n equals 40. Right? See how it's getting bigger by 10 each time? And then where do I want you to stop? At n equals 1000. And you can see 1.5, 1.0049, and then it's just ones afterwards, right? Do you see how basically at some point it's basically telling you, like, look, all of those basically just round to 1. As you head off towards infinity, it looks like the value is going to 1. Okay. There's some other really nice tools here that you can use. There's a tool called Discrete Plot. And that allows you to get like a graph of this. Wow, I'm just having a hard time typing with this. It's like way harder than I thought it would be. So the way the discrete plot works is that you put in the curly braces 1, all the way up to the last number that you want it to plug into. So let's have it plug in from 1 to 100. Why is it not letting me do that? Oh, I think I have to do n 1 to 100. There we go. Okay, it's a little hard to see. Okay, let's not do n to 100. Let's do n 1 to 10. There we go. So you can see my first point. Do you see out there? You can see the dot at 1.5, and then above 2, you can see the dot at like 1.25. And so do you see how the dots, they're heading down towards close to the value of 1, right? Do you see how the scale is from the scale starts, the y value starts at 1 and ends at 1.5. So you can see that they're slowly heading down towards 1. Okay. So this it allows you to sort of look to see what's happening to the values. Okay, so that's how you can do it numerically. Most of the time, however, you're not gonna do it numerically. We know how to evaluate limits analytically, right? So we can do that. So normally to figure out that that's gonna go to 1, you would say, hey, I'm gonna take the limit as n goes to infinity of 1 plus 1/2 to the n. Now, what's the limit of 1 going to be? 1. Now, what you have to figure out is, hey, what happens to the limit as n goes to infinity of 1/2 to the n? As you keep on doing 1/2 raised to higher and higher powers, what do we know that that goes to? Like half of a half of a half of a half. We know that it goes to 0, right? Which is why it makes sense that the limit of that sequence ends up being 1. In other words, as you keep on going further and further down the list, it looks like all of those numbers keep on getting closer and closer to 1. Okay? Which is what happens. Right, exactly. And the bigger the end it gets, the smaller, the more minute this value becomes. Exactly. So one of the things, so the way we write this is we would say like, hey, what does it mean for the limit as n goes to infinity of an to be equal to some value L? That means that as you go further down the sequence, what number are the terms in the sequence getting closer and closer to? L. Now, if you think about what that means, like this is what it means, like if you were to plot it. Yeah, because you take the limit of 1 plus the limit of 1/2 to the n. I use the limit rule. So yeah, you have the limit of 1 plus 1/2 to the n, and that splits into the limit as n goes to infinity of 1 plus the limit as n goes to infinity of 1/2 to the n. Notice I just didn't write this step because I just knew that the limit of 1 would be 1. But this one is right there. Okay, so what does this mean? If this is your line y equals L, for the limit of an as n approaches infinity to be equal to L, what it's telling you is that after a certain point, after some index j, let's call it, all terms after aj are within a distance epsilon of L. So what this is telling you is, let's say that this is j right here. Once you go past this point, the furthest away any of your terms are going to be is some number epsilon. So this is L plus epsilon This is L minus epsilon. So in other words, every single point afterwards never leaves this box. And as you go further on to the right, they're getting closer and closer to that green line. Now before that box, they may be like way out here. Do you see how like from the first couple terms, do you see how they're outside of that area? They're like these big values. But as you get closer and closer, what are all these dots? As your index gets bigger and bigger, if you look at all those dots, do you see how they're converging on that green line? That's what it means for the limit to be equal to L. It means like, look, let's say you choose epsilon equals 1/2. That means you can find a cutoff point at some point in the sequence, anywhere past J, the terms are never more than 1/2 away from L. Okay, so they keep on getting closer and closer and closer and closer to it. This is why that discrete plot is really useful, because you can sort of see where they're heading towards. The discrete. This is like the discrete plot that I showed you. Okay, now all of those limit laws that you learned in the past are still applicable here. So you remember how like the limit of a constant is a constant, the limit of f plus g is the limit of f plus the limit of g, or like constant multiple rule and all that. All that still applies here for calculating these limits. So we're going to use that. So like, yeah. This is chapter 5, I said. So, like all those things you've learned in the past, like the limit as n goes to infinity of some constant times a to the n, you can factor that constant outside of the limit and then compute the limit of a to the n. If you have the limit as n goes to infinity of some sequence plus or minus some other sequence, what you can do is calculate the limit of each sequence independently and then add or subtract them. Right, so these limit laws should be sort of familiar, right? You can factor out constant multiples. If you have two sequences being added to make a new sequence, you can just add one sequence plus the other sequence. They're pretty straightforward. Let's say you have one sequence times another sequence. Like what you can just do is do the limit of one sequence and then multiply that by the limit of the other sequence. Let's say you have a new sequence that's one sequence divided by another sequence. You can take the limit of the top and divide by the limit of the bottom, as long as the bottom is not what? 0. Yeah. So these limit laws that you learned in 101A, or hopefully you learned in 101A, well, I think for most of you, you're pretty good because Professor O'Connell is like really good at this stuff. I'm pretty sure you covered this stuff. And I know that a bunch of you came from his class, so like there's a bunch of you from OMG, right? Is this the class that I have like a lot of the OMG people? Yeah. Okay, cool. So you can use all of this to calculate these sorts of limits. So like quick example, let's say you were doing the limit as n goes to infinity, yeah, with let's say your new sequence is 5 minus 3 over n squared. Well, the limit laws tell you have basically the difference of two sequences. One of your sequences is just the number 5 over and over and over again. What's your other sequence? You come up with it by taking 3 and dividing by n squared, where you plug in n equals 1, plug in n equals 2, plug in n equals 3. So we now know that you can just split it up. The limit of 5 minus the limit of 3 over n squared. Okay, well, we know that the limit of 5 is just 5. And then what do we know about 3 over n squared as n goes to infinity? What's going to happen to that number? Because the number on bottom is going to get what? So yeah, the whole thing's going to get smaller because the number on bottom gets bigger and bigger, so you get 0. So in other words, if you were to look at the sequence of 5 minus 3 over n squared, those numbers are going to get closer and closer and closer to 5 because it's 5 minus a smaller and smaller number. Yeah, so we use the fact that, yeah, your original sequence is 5 minus 3 over n squared. You come up with the terms by plugging them into there. If you go to infinity, those numbers are going to get closer and closer to 5. How did we figure that out? By using the limit properties. Likewise, what could you have done? You could have gone back to Mathematica or Wolfram and had it like plug in numbers, right? 1, 2, 3, 4, 5, up to 1,000. You'd see that they get closer and closer to 5. Cool. Okay. I think this is a good place to stop then.